Okay, so for today, we are going to discuss on the hands-on detailed applications, which basically an introduction to CFD procedure. So last week, for the past 2 weeks, we talked about the introduction to CFD, the philosophy, why we need to study or to learn CFD. And today we are going to start looking at the CFD procedures, which is important because it will be used for your labs. Okay. So for today, hopefully in this session and for the next 2 weeks, we are going to finish this hands-on detailed applications, introduction to CFD, the procedures in terms of theory in lecture, as well as NCs for the lab. Okay. All right. So if you can see over here, so the questions that we all have is how to achieve this kind of results. So it looks nice, it looks beautiful, but the question is, how can we achieve this? Okay. So the answers to that: practice, 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 and using the right tools. So I think it reflects back to what Mr. Azmil just shared just now. So it took him months to basically understand the simple concept of what he's trying to solve, and then another a year and a half to practically understand the whole simulation purposes, as well as to masterly use that particular software. Okay, and I would like to add some more points on what Mr. Azmil just said just now in terms of practice. You also need to use the right tools, meaning that if you can see over here, we have a bunch of options in using the simulation software, either open source or commercial package. So if you can see here, we have, for example, commonly used is Console, we have SolidWorks, of course, we have SimScale, we have ParaView, NCS, Telemac, and so on and so forth. So the question is, for example, if you are going to do CFD analysis, or maybe FEA, for example, are you going to use the same software as CFD? So it might be not. So make sure you understand these problems that you have and the tools that you have in hand. Is it suitable to be used to solve that particular problem? Okay. So the objective for this session is, first one, to understand the importance of a high quality, good resolution mesh. And then we're going to see how to apply appropriate boundary conditions to computational domains. We're also going to have a look at understanding how to apply CFD to basic engineering problems and how to determine whether the output is physically meaningful. So again, I talked about this in detail last time. If you have some input, you're pretty much guaranteed to have an output. But how do you ensure that the output is physically meaningful? Is it reliable? Is it acceptable? So that's what we want to have a look. And then we're going to, at the end of this session, you are going to realize that you need much further study and practice to use CFD successfully, which is again what Mr. Azmil just said just now. If you think just by doing 1 or 2 labs should be sufficient and you call yourself master, so you are way off the mark. Okay, because CFD, it needs practice, practice, and practice. So I did my master's project using CFD, and then I also did my PhD for 4 years using CFD day in and day out, and yet up until today I will not call myself an expert yet, because there is so much more that I have to learn, I have to practice in order to completely master CFD. Okay. All right. So let's have a look at these two pictures that we have on the screen. First, if you look at this one on the left, so this is what we want. Basically, for example, you have a body here, and you are interested in looking at the flow passing through the bodies, which is quite similar to what you're going to have for your second lab. All right. So if you see over here, the mesh has been generated quite nicely. So, for example, why I say this is what we want. Okay. So the focus of our interest in this case is the body here and the flow behind the body. Let's say you are interested to see at a certain distance. Okay. So the mesh has been refined, heavily refined, I might say, for the region next or close to that particular object. Okay, in this case, the cylinder. Okay, so it has to be, for example, the upstream of the body. We don't take too much space, so just a bit upstream, just to capture the deceleration. And then we are interested to see the wake. So the wake has to be fully merged or fully recovered at a certain distance. So we want to see that. So it has to be slightly longer than the upstream. So we have a very highly refined unstructured grid over here. And then because we are only interested at the phenomena or at the situation behind the object, we don't care much about the domain outside here. So for the domain outside here, we can use a coarser grid. A coarse grid means a grid that has higher dimensions compared to the refined grid. Okay, so we have refined, which means very, very small, and we have the coarse grid. Coarse, which means a mesh or a grid size that is slightly larger than what we have over here. Okay. So this is quite a beautiful mesh. So now, if we look something over here, this is for FEA actually, it's not CFD, FEA. But let's look at the value of the displacement, which is given over here. Let's say we are interested to look at the displacement at the top left corner over here. Okay, now we have four similar objects, but with four different meshing criteria or meshing setup. So we have the first one, second one, the third one, and the fourth one over here. And let's look at the value that we have over here. Okay, so if you notice, the value deviates or is different from one simulation to another. Okay, so now why we have a different output while having the same dimension for the same object? So the answer is because we have a different mesh setup. So if you can see over here, okay, which one of these four pictures or four objects that you think have a better or a good mesh setup? Okay, so by looking by naked eyes, by looking at the mesh setup, we would say the left one has a better mesh generation. Okay, because later on we are going to learn about mesh skewness. We are going to learn about the interaction or the combination of structured and unstructured grid. What is the best mesh generation possible? We are going to discuss that later. But by naked eye, we can see that this is the object that we have, and the mesh basically is being nicely represented and nicely spaced throughout the object. If you see over here on the left, you can see some deformation is happening on the object because of the mesh. If you see over here, the mesh is different in sizes. Although it's not wrong, we have a different sizes in terms of grid generation over here. But over here, if we are interested in a small body like this, just one particular corner, the mesh should be generated uniformly. Okay, so now we have uneven distribution of mesh, and you can see that we have red displacement, meaning that we have highest displacement at this particular region. Okay, just one corner of it. And next, again, this is again a poor mesh generation because the orientation is not consistent. We have sometimes the triangle facing to the right, sometimes is facing to the left. Okay. And again, on the right side here, the last one on the furthest right, the mesh generation is again poor because it's not evenly distributed. So this is what we are going to discuss in this session, basically the importance of mesh generation. Okay, so if I can just quickly summarize the general solution procedure for CFD, it can be given in terms of this body or the flow on the left here. We always start with problem identification, where we define our goals and we determine and identify our domain. Okay, so the details in terms of selection of geometry, we are going to decide on the parameters, also of course the sizes and shapes of our domain. Okay. Once we identify our problems and also we have the domain that we want, we can next proceed to pre-processing. Pre-processing means setting up the calculation or the computation. You have a domain, now you need to input or you need to put some values to the domain. See? So you have a geometry. So this geometry basically the domain that you have and also the object that you want to study, for example. And then we proceed to mesh. So once you have a domain that you want, you have an object in the middle of the domain, for example, the cylinder just now we have. So you want to create a mesh that represents the area that you are interested in. So for example, just now, if we are interested in the area immediately downstream of the object, so we focus our mesh to be highly refined just at the immediate region that we are interested in. Because if we create highly refined mesh for the whole domain like this, for example, it will take too much computational power, okay, meaning that it will take too long to compute and you need more computational resources to finish the calculation. Then, of course, we need to set our physics. Okay, remember, we need to put some setting. We need to decide, is it going to be, for example, the accuracy of iteration. How do you know whether 10 iterations or maybe 1,000 iterations should be enough for that? So that's come from experience, but that's all in the setting. Then in the pre-processing, in setting up your domain, of course, this is where you decide whether your work involves heat transfer, like Mr. Azmir's work before. If you are dealing with furnace, for example, then you know it involves heat. Then of course you have heat transfer. So this is where also you need to put the initial conditions. Okay, at the start of the calculation, what is the condition of the object or the domain? Then you decide on the boundary conditions. Okay, what is the property of the wall? Is it going to be shear? Is it going to be smooth wall? And then, of course, flow properties, set the viscous model, and the fluid properties. Is it compressible or incompressible? And in here, of course, we can decide to use either unstructured mesh, structured mesh, adaptive mesh. Adaptive means the combination of these two. Okay. Next, you proceed to solving the computation. Okay. So in solving the computation, you have several options. You can choose either steady or unsteady calculation. Okay, most of the time we are dealing with steady because it's easier to solve. Okay. Unsteady means your calculation changes over time. I'm going to show later on in this course the difference in setting up or the difference in the output, the comparison between steady and unsteady calculation or simulation. And then we have to set our iteration or the number of steps, the convergence limit, the precision or the numerical scheme, all this in computation part. And then we go to post-processing, which is just as important as the first three steps. You can produce any output which is nice to the eyes, but in the end, how do you visualize or how do you examine? So you can examine, you can analyze, explore your output, okay, either by using XY plot, and you have to verify again, of course, and validation. We discussed this before. You can either look in terms of vectors, streamline, or contour plots. Okay, and of course, you can set the output to be in terms of velocity, pressure, turbulence, so on and so forth, depending on the problem that you may have. Okay, but I'm going to show you later. We are not going to just stop at post-processing. Okay, remember, we have to check the reliability, the accuracy of our result. So how to check that? Of course, based on experience and validation with experimental or theoretical data. So from there, if we notice any deviation or error, okay, then we can proceed to updating our model and we go back, okay, either to the pre-processing or start all over again from the first. Okay, we identify our goals and set the domain. Okay, so it doesn't end at post-processing. Always remember that. The CFD process always involves iteration, meaning that you arrive at this step, you get the result in terms of contour plot or streamline plot or vector plots, then you analyze, you decide whether they might need some update in terms of the input. Maybe your mesh is not small enough, for example, it's not highly refined. Maybe you want to update your physics, for example, the numerical scheme that you use. So it always needs updating in terms of the processes. Okay. All right. So let's start looking at the procedure one at a time. So if we have a problem, something like this, okay, this is related to my research interest. If you are given this particular problem, I ask you to model a tidal turbine. Okay. How are you going to proceed? So we have a problem. Okay. So you have a problem, which is you have to simulate a tidal turbine. Okay. How are you supposed to proceed from there? Okay. So first, when you have a problem, you need to set the domain. How can you transfer from a working application, something like this, to something that can be analyzed or simulated in a domain in CFD? Okay. So next, you need to do first one to decide on the domain. We are still talking about the problem identification. So this is the problem. Then you need to decide on the domain. Okay. How can you decide on the domain? You have to make some assumptions and simplifications. Do you really need, for example, to model the blade in this case? Do you need all the structures, for example? Or do you need, for example, to look at the detailed applications to see the weight interaction, for example? So what is it that you need to do for this particular problem? So it depends on the problem. If you are just interested to look at the flow interaction or the vortex mixing or the wake, what we call the wake. Basically, if this is the inlet from the left and this is the outlet from the right, you're just interested to look at the wake formation, meaning that you have an inflow and then you have a deceleration, okay, because you have an object, okay, and then you want to see how long does the flow needs to go downstream to recover the initial velocity of the inflow. If you just want to do that, you do not need, for example, the details of the structure. You do not need the details of the blades design, for example. You can just make a small rectangular box like this as your domain. We can call it a channel. Okay? And your object, your tidal turbine, is now being simplified to just a circular disc. If we are dealing with horizontal axis tidal turbine like this, for example, we have several methods to simplify the object or to simplify the problem. We can either make the simplest assumptions, which is basically, tidal turbine, when it rotates, it will be in terms of circular motion. So we can assume it to be a circular disc. So we call it actuator disc. So that's one of the methods. Okay? Because you are not interested to see the interaction of the flow between turbines, the blade, and also the flow. So you do not need the details design of the blade. You just can assume the tidal turbine to be a simple circular model. So that's just how you approach CFD problem. If you just want to replicate, to design exactly as the problem that you face, for example, over here, then you have to include the detail structure, the dimension of the support structure, for example. So over here, all that is being neglected. Okay? You just draw a simple circle that represents the tidal turbine because you're just interested in the weight. So see how some problems that involve structure, we have all these holder, nestle, the blades, all that is being relegated, simplified to just a circular disc. Okay? So that's for the first step. You need to make assumptions and simplifications. But of course, later on, we're going to discuss how simple can we simplify? How far can we go to simplify our problems? Okay, we have to decide that. We need some knowledge on that. So the next process, pre-processing, is about setting up your model. So again, this is okay, the one I just want to highlight over here, the one that is in the purple box, or the purple box over here. They are all from the work done by my student as well as my previous study. Okay, so these are all real data, real figures from my students, for my FYP students, as well as from my previous work. Okay, so for example, over here we are going to set the mesh, for example. Okay, for example, that we have, this is domain. Okay, the schematic of the domain. Please pay attention, because this is quite similar to what you are going to do for your second lab. So you are given a schematic of a domain. Okay, you have an object over here, and you want to see how the flow behaves passing through the object. So the object here, this is a cylinder. Okay, so the cylinder over here, if you can see over here, these are two types of mesh setup. One is by using an auto-generated mesh, by using global meshing, meaning that you just click the button in ANSYS, the mesh will automatically be generated. You just specify the value that you want. Okay. The other hand, you have the localized meshing in ANSYS, meaning that because we know that this is the object of interest, okay, because we want to see the flow interaction between the inflow, the flow around the object. So we know that we need to make the mesh around the area of interest to be more smooth or more refined. So we use a globalized, instead of using globalized, we use the localized meshing setup. So you can see the difference. If you use a global meshing, you can see how coarse or how big the element is within the object. But over here, we can see that after refining the face, the edges of the object, you can see we have several hundreds or thousands more elements within that particular region compared to this. This we can count 1, 2, 3, maybe just about 8 elements compared to these thousands of elements. So we are going to discuss later how that will influence the accuracy. Okay? So another thing, the choice and quality of mesh will influence your simulation. Okay, so for example, over here, we have, this is a global setting, and this is a localized setting. See the difference in terms, this is not globalized setting. This is unstructured grid. Okay, this is unstructured grid, and this is structured grid. Okay, see the difference between structured and unstructured. Unstructured, it formed quite nicely along the face, okay? Or maybe the edges. So sorry, this is the edges, this is the face. But because of a circular object, the circular geometry, the structured grid have a difficulty in terms of the face generation. Okay? So you can see over here, the mesh itself is quite okay, but you can see it's no longer a perfect square or rectangle. Okay, so now you have some skewness. So this is skewness that we are going to discuss later. So compared to that, this is unstructured grid. So unstructured grid, it can capture the complexity of any geometry that has curves, that have corners, for example. Okay, so so you can see the difference in choosing your mesh. If you use one mesh, yes, you still get the grid generation, but the quality will be different. So we are going to, hopefully from the labs, from the lecture, we can get some idea when to use which of these two, or maybe the combination of these two mesh in your practical study. Okay. So next we go to solution, where we are going to look at basically the iterations, how many iterations are needed to solve that particular problem. So if you look over here, we have several graphs. It looks so confusing at first. But over time, once you have done one or two labs or simulation, you will get some idea the importance of this line. So this plots basically just to show the convergence. Okay, if you notice the bottom plot over here, this is the commonly produced plot for most FYP work. Okay, but not to say that these two plots are wrong. For example, if you are dealing with something that is dynamic, for example, instead of a static object, cylinder just now, but now you have a rotating cylinder. Okay. Now, when you have a rotating cylinder, you have to use a different mesh setup. Instead of static, you need to use the dynamic setup. So when you use dynamic setup, the plot will no longer look like this. It will look something like this. So it's important to understand that not all applications look alike. You cannot say, okay, this is my work. This is what I get for my mesh convergence or convergence study or convergence plot. You cannot say that because your work might be different from the other students. Some students might get this plot, for example, and you cannot say, oh, this plot is wrong. You cannot say that. You need to understand what the problem is about, whether this is what you should be getting at. Okay, so you need to understand that. And of course, finally, for post-processing, we discussed this before. All these beautiful pictures about what are the meaning of this. This is the streamline, for example. This is the vectors, and this is the color contour. If you have no idea what you are dealing with, if you have no idea, for example, what Mr. Azmin said just now, you have no idea or no understanding of the first law of thermodynamics because he's dealing with furnace, okay, heat. So first law of thermodynamics. In our case, we are dealing mostly with CFD. If you have no idea about the fluid mechanics, how the fluid behave, then you have difficulties in analyzing the plots or the output of your simulation. Okay, so this is the question that you always need to ask yourself: how do you verify your results? Okay? It may look good, but it doesn't mean that these plots are correct. Okay. Okay. So what we have over here, so last time we discussed about the CFD black box. And what I have over here is the finite element process. Okay, I'm going to give you about 30 seconds just to have a look between the CFD black box and the FEA process that usually is used to run or any FEA simulation. Just take about 30 seconds. Okay, so if you notice, what we discussed before is being captured or is being presented again as quite a similar procedure for the FEA. So regardless whether you are doing FEA or CFD, any simulation basically will involve quite a similar process. So for example, this is what we just discussed previously, and this is for the FEA process. So we have the physical problems, we have mathematical model, we need to decide, okay, basically how to represent our problem into a mathematical model. And then we need to have, of course, the finite element solution in terms of the meshing, of the solution parameters, the boundaries. Okay? And then we have the assessment of accuracy, which is post-processing over here. So we need to go back. If you think there is a deviation or the physics doesn't add up, so you have to go back. Okay, for example, maybe you need to refine the mesh. Okay, and then you have to interpret the result all over again. Okay, it is a loop. It is an iteration. The process is always an iteration. Okay, so you interpret the result and then see whether you can make some improvement on the result. So this is what your case study looks like. You have an object, you make a simulation, then you need to propose how to improve the object that you have or the problem that you have. Okay, so just to recap, modern engineers apply both experimental and CFD analysis, and the two complement each other. So again, I emphasize this over and over again. We need to have both experimental and CFD, and also maybe analytical to complement. Okay, because we need to validate the CFD analysis. Okay. All right, and then in addition, the experimental data are often used to validate the CFD solution. Okay, we talked about this before. So again, I shared these pictures over here of Hidden Figures poster, because if you watch the Hidden Figures movie, you will notice how, even with the availability of the IBM machine in this case, in the 1970s or maybe 1960s, in the end, humans still plays a major role in validating the calculations. So we cannot put 100% trust in the simulation, even though we are an expert in that particular field. Okay, it needs to be verified. Okay, watch this movie and you will understand why. So in the end, CFD is then employed to shorten the design cycle through carefully controlled parametric studies, thereby reducing the required amount of experimental testing. So in the end, we use CFD because we want to shorten the design process, the design cycle. Okay, and of course, in the end, the cost involved. Okay. All right. So I think we discussed this before. CFD is basically, aside from the beautiful contour that we look at, it is governed by the Navier-Stokes equations, which is based on the continuity equation. So if you don't remember, continuity equation is the conservation of mass. Mass basically is preserved, and also conservation of momentum, basically F equals to ma. Okay, so the symbol that you have over here that you will encounter from time to time is basically the vector operator. So V here, it refers to the variables. Okay, so this basically is represented by what we have over here, the equations. P here, it can be T, it can be V, it can be P. Okay, it's just a variables. So it is basically the D variables divided by dx or dy or dz. So this is what the vector components mean. Okay, so don't worry too much. After we finish this lecture on the CFD procedure, we are going to jump into the derivation of the Navier-Stokes, meaning that we are going to revise, we are going to look again how we get to continuity equation, how do we arrive at this equation, how do we arrive at the momentum equation, and finally how these two equations are being used to get the Navier-Stokes equations. So there should be an S, it should be plural because it is a combination of momentum, continuity, and also the energy equation. Okay, so as all things that we discussed for engineering problems, if you notice, if you realize from thermodynamics into fluids, there will always be assumptions. That's why assumptions are very, very important in engineering. You need to specify your assumptions before you start solving that particular problem. So in this case, the Navier-Stokes equations that we have over here is based on the assumptions that it is a Newtonian fluid. Okay, it is Newtonian, and it is based on constant properties and without free surface effect. So it is Newtonian. Okay, and then from these equations, we have 4 equations and 4 unknowns, which is U, V, W, and the pressure. Okay, so this is what we are trying to solve basically for the Navier-Stokes equations. Okay, so apart from Navier-Stokes, so this is our end target. We will also look at basically how the Navier-Stokes differ or difference from the Euler equations. Okay, how the Navier-Stokes can be derived by including the viscosity term, and how from F equals to ma, we are going to derive the momentum equations. Okay, so it's now 4:30. So I'm going to stop our lecture for today on this slide. So there will be no asynchronous session because we have lab this week. So hopefully we can all meet again next week for the lecture session on Wednesday. But remember, we still have the lab for next week, and please do not forget the attendance. I'm going to record about the next for the next 30 minutes. We still have 30 minutes remaining. I'm going to record further 30 minutes of video and post it as a synchronous session, okay, as part of today's lesson. Okay, so before we end, anyone has any questions?
Sure.